Okay, so I think now what I'm going to do is I will try to demonstrate you all the physics that can be done with this kind of formalism, and discuss some other more general aspects. So let us start with a simple model. I can illustrate this whole story by taking a simplest case, which we can, since we're doing physics, we can discuss as lithium-11 model. Now, you have a homework where you can actually discuss a model of two spins and address the same questions of what happens when the system is unstable. So what's lithium-11, in terms of the simplified picture, you can say, well, this is lithium-9 as a core, and assume it's completely stable with no degrees of freedom. And then you can have two nucleons outside, and they can be either on p1/2 state or s1/2 state. So this is now a system with two states. Now, remember, this is different from the one particle in the well that we were discussing. Right now we're talking about two particles, but these two particles interact, so they sort of bind themselves into pairs, and this pair can be either here or here. Okay, so then our space is just a 2x2 matrix, so we only have two states, and state 1 and state 2. So then our general effective Hamiltonian, which is this in the p space, can be written as a matrix. So this is a matrix which has energy 1 and energy 2, which is the energy of this state and energy of that state. Then there is a pairing interaction. So these two pair can move. And of course, pair has angular momentum 0, so it can easily move from one orbital to another orbital. So, and this pairing interaction is Hermitian V. Now, you can also say that, of course, from both of these states, this pair can decay. And as you know, lithium-11 is unbound, is slightly bound, so it's very closely bound, but then there is another resonance there. So it can decay, and this decay is described by gamma 1 and gamma 2. Okay? And of course, these, in our formalism, we had this matrix A dagger A. So we have gamma 1 is just A1 squared, and gamma 2 is just A2 squared. So this way we're going to get a non-Hermitian matrix W, which is completely factorized. Okay, so now this is my model, and I can vary this model and see what happens. So there are quite a few interesting things happen, but I also remind you that these decays, if this is a p-wave decay, which is described by gamma 1, then it's some constant time energy to the power of 3/2. Right? We also talked about that the phase space is L plus e to the power of L plus 1/2. So for S wave, the decay is square root of energy. Then we can take threshold at 0, and there are various parameters here. So let me show you what happens. This is also reaction, what I just described you, but I'm going to skip it. So what happens is, if I take this matrix, if you have a normal 2x2 matrix, what happens if you increase the real off-diagonal part? So if you increase the real off-diagonal part, two states push away from each other, right? Which is a standard Wigner repulsion of two levels. Easy to show. So when I am increasing this V, these two states go away from each other. And at some moment, the lowest state is going to cross the threshold, and it will become bound. Okay, so let's see what happens. So this is this picture as a function of V. What happens? There are two states, there are energies, and then there are their widths. So here they repel each other as I increase V. And in the lower plot, you see the widths. So whenever I reach critical, this blue second state becomes bound. But the other state is still unbound. Now, an interesting situation happens is if I change phases of these amplitudes. Because I said amplitude A1 and A2 are proportional to their corresponding phase spaces, to square roots of energies or powers of energies. But I didn't specify what are the relative signs of those two. So if I change the sign to opposite, then you see in energies, picture is similar, but there is a very interesting situation in the widths. So while we are still above critical, so which is critical somewhere here, you see that the width of the state can be exactly 0. So there is a possibility to actually have an destructive interference in such a way that one of the state, even though it can decay, does not decay. Okay, which is an interesting story from old times. Here is there was a question actually, can you have a potential in the one-dimensional potential so that it has a bound state, whereas this bound state is above the asymptotic, so the potential goes to 0 far away, but you have a bound state at the energy above 0. So, and this is an example. Actually, yes, it's possible. So there is a state here in this oscillatory potential. This state is bound, it has no width, because of interference. So you have waves going that way and then reflected waves going backwards, and then they interfere, killing the outgoing flux at the end. Okay, but now talking a little bit about physics of this interacting resonances, what happens is when you have two resonances in this form, then if you increase the real part between these two resonances, such as shown here, so if I increase my real part, then the resonances will be pushed away from each other. It's like the standard Wigner repulsion again. If you increase the real interaction between states, the states get pushed apart. At the same time, states being pushed apart generally means that their widths will be almost the same, so which is separation here. However, in reverse, if you increase the imaginary part, then increasing the imaginary part will bring states closer, and it will lead to another effect that one of the states of the two states will have larger width and the other one will have a smaller width. Actually, I can show you that briefly in the simple demonstration. If you think of the matrix, I mean, all of this can be done analytically with that general matrix, but if you think in a simple way, if I have a matrix gamma, so let's say energy 1, which I just call energy minus I over 2 gamma, and then you have some interaction V here, and then let's put the other state as 0. So this is going to be my matrix. If I would like to find the eigenvalues of this matrix, then this is E eigenvalue equation that I will get I gamma over 2 minus my energy that I'm looking for, multiplied by minus energy here, minus V squared equals to 0, right? So this is the eigenvalue equation that I will get, which is my energy squared minus I gamma over 2, and then minus V squared equals to 0. Right, so this is a quadratic equation, and the solution is energy equals 1/2, and here we'll have this E minus I gamma over 2 plus minus square root of this term squared, which is E minus I gamma. Well, let me write it explicitly. So this is E squared minus I gamma E over 2 minus gamma squared over 4 plus 4V squared, right? So, and you can see what happens with this equation at various limits. So the interesting limit is when my width gamma becomes very large. So when the width becomes very large, then the most important term under the square root is this term, minus gamma squared over 4, which is negative. So here I would have the following, that the very strong coupling, so to continue when the decay is very strong, what I will have is that my energy has some real part which I'm not interested in, and then has, imagine, minus I over 2 gamma, so this is 1/2. So this is for gamma goes to infinity limit. I only have gamma, so I have this term, and then plus minus square root of this term, which is just I over 2 gamma again. So you see, one energy with the minus sign will be just the full gamma over 2, and the other width will be 0. So I'll have two states. One is going to have width I over 2 gamma, and the other one will have width 0. Okay, so that's one thing. Another thing which I was saying already there, that what is, if I'm talking about gamma being relatively small, so here I will have width or the separation between these two signs, plus and minus, and assuming this is real. So I will have energy squared plus 4v squared. So essentially a real part here is E squared plus 4v squared minus gamma squared over 4. So that's the real part. So this real part increases when V increases, which is the standard Wigner repulsion, but decreases when gamma increases. So increasing width sort of pushes states closer to each other, right? And this is what I am illustrating in this picture, right? So that this this real part and imaginary part act in the opposite way, in a sense. Okay, so this is a general dynamics. I just wanted to illustrate you with some pictures of the in various cases. So there is a possibility that your imaginary parts can cross, and then there is a possibility that real parts can cross. So because of that general behavior. So now we have a more general problem where you have two resonances. So they can't have the same energies in principle. Okay, and these are some conditions for crossing, which I think I'm going to skip right now. So we can study the reaction cross-section. This is in the same model, two levels showing reaction cross-section and various combinations. And you can even have, so this is when one state is bound, so you can have an attraction to this bound state. So this is an example when one of those two states is a bound state. But like we discussed earlier in the lectures, if you have an S-wave state close to threshold, then your cross-section has this behavior, which is, we saw that before. So your cross-section as a function of energy will have this kind of behavior, where this distance is proportional to scattering length. Right. Okay, so, and of course, maybe I should put the units here. So this is the energy, this is the cross-section. Okay, so that's some examples. Then for this two-level model, I can also address the time dependence, because we discussed in this course the time dependence, and these are different combinations, but these are two resonances under various conditions. And what's interesting also that you can have an oscillatory behavior in this survival probability. And again, remote behavior, as before, is a power law, and we have an exponential behavior. But because of interference of these two resonances, this exponential behavior is not exactly exponential. It's modified with these various oscillations, right? So, and these are different curves here corresponding to different choices of parameters, and the corresponding time dependencies are shown below. Okay, so overall, when you have a channel, like in this example, when you have a strong gamma, what happens is, of course, your states are coupled to each other through this gamma. And this limit, when one of the when the coupling is very strong, is referred to often as a superradiance limit. And the idea of superradiance comes from the similar effect in optics, when you have many atoms, and all of these atoms can have an excited state, but they all can decay with a photon, and they share the same radiation field. So even though the atoms are separate, they share the radiation field, so they can form essentially a collective decaying state. So there is one many-body state that is very collective and in some way oriented towards decay. And this is what I tried to illustrate here. There could be many, many states, and all of these states are coupled to a given channel. So they have the same coupling to the same channel. So they can have, therefore, essentially a common interaction. Now, you can also understand this, what happens, why we have this effect is from the structure of this matrix, that the matrix W is factorized, and because it is factorized, you know that the factorized matrices have fewer eigenvalues, right? So they mainly have 0 eigenvalues, and the number of non-zero eigenvalues equals to the number of channels. So therefore, you have a special component in your Hamiltonian that is somewhat a more trivial matrix. All right, and let me give you this example, which you can also do on the computer. So this is an example of a many-body system. So we take several bound orbitals, and we put, in this example, I had 8 single particle orbitals and 3 particles. Very simple system. Put some arbitrary interaction and say that only upper particle can decay, and vary the decay width of this upper particle. So all particles interact between themselves with a Hermitian interaction, but whenever particles on the upper state, it decays. Again, this is the same problem as almost in your homework. So this is the plot of all widths as a function of energy, and they're plotted sort of in the continuous lines as we increase this single particle decay. So this, now I'm talking about 2 different gammas. So there is one gamma here, which like in this model was gamma here. These widths that I obtain here, I call it capital gamma because these are many-body widths. So I had one particle decaying, but whenever I put it in the system, the whole many-body states, the state of many particles, can decay. And the question is, what is the decay of that state? So these are all of these energies of the states in the complex plane and how they evolve. So what you can see that some of the states actually go down quickly, and some of the states come back to real axis. So, and this is this effect which is related to this factorized form of A dagger of the W matrix, that there is a separation of states into the ones that become very broad and into the ones that become very narrow. So in fact, it's also related to a direct and compound reactions that people often refer. So there is a general scattering over the broad states, and then you can populate the nucleus, some resonance state in nucleus, which lives for a very long time because it's almost decoupled from the continuum. So this is a similar effect, and if I magnify this, you see the crazy evolution of all these states. But these are the states that come back to real axis. And of course, they can cross in the complex plane easily. All right, now in relation to this, there's been a lot of recent experiments related to alpha particles. And what has been observed with alpha particles is some very broad states. So, and this is the example of some very broad resonances observed in oxygen 18. So basically, this is the list of states, and these are what they call their reduced widths. So the reduced width here is the ratio of the width observed towards the width predicted in the simplest potential model. That simplest potential model can be like a Wood-Saxon potential. You put a particle in there with the correct parameters related to charge and the mass of an alpha particle, solve it, and find the width. And you take the ratio, and you see if this ratio is close to 1, such as in this example, then this state saturates almost all possible decay width because it's nearly 1. Otherwise, you would expect the width to be fragmented around many states. So, and now, talking about realistic nuclei, carbon-14 plus alpha, oxygen 18, is an open shell nucleus. So it has a lot of states. And it's not obvious why a single state has all of the width, whereas all other states are so narrow. So, and that's what is essentially addressed here and discussed in context of this separation of widths, that some states become very narrow, some states become very broad. Yeah, so this is a more detailed picture proving that there is this resonance. So if you have this is with this red line, if you put this broad resonance, then the scattering data at various angles is described very well, which is this red line. And if you don't put this resonance in, then you get a blue line and you see disagreement. But it's very hard experimentally to prove the existence of such a broad state because you don't see it as a resonance. Okay, so now this approach is commonly applied in the nuclear shell model, so which is then referred to as the continuum shell model. So briefly speaking, nuclear shell model, as I already mentioned several times, you put many particles in the harmonic oscillator shell or in some mean field potential, and you solve this problem as a bound problem. So I know next week there will be more shell model discussions or lectures, so you will address more details there. But now you can supplement this nuclear shell model with this continuum and address, again, the same question: what happens, how do the particles decay? Which is just an illustration here. Okay, so I talked about the theory, and this is just a reminder, exactly the same steps. So you modify your Hamiltonian from what we discussed already. All of these terms should be familiar here. And you have a T matrix. So what are the channels? Maybe channels I should address. So in your shell model, in the many-body picture, the simplest channel is the one-body decay, when you have either proton or neutron in the continuum, and you have your daughter nucleus in its eigenstate, so which would be a natural simplest channel. So then in that case, if you have this as a channel, then your interaction potential, again in the simplest picture, would be a one-body mean field, because this is a one-body channel that takes your particle from inside into the continuum. So, and one-body mean field can be modeled again by let's say Wood-Saxon potential, any potential that has a continuum. So then maybe important statement here is about the channels, is that if you look at our problem and assume, so we have a channel and we can define this channel state. So we had channel, which it has a function of energy, right? So this amplitude was a state which is bound between an overlap, sorry, this is my potential V here, between a continuum and the bound state. But this channel is almost a product between some final state F, which is a bound state, times the continuum, a single particle in the continuum. So if that's the case, then this becomes your complete state for the parent system, some interaction potential, which is usually taken as a mean field potential, times this final state multiplied by this E. So, but what happens is this works, potential V, works only on one body particle. So you can in fact think of this as a channel vector. So so if you go through all the bases 1, and this 1 is a basis state. So therefore you can think of this channel as a state in my P space, which is just some amplitude A for this one being removed, which depends on this energy E, multiplied by some fixed state, which is, yeah, I guess it's a bad writing. So this is my full channel, which depends on E, and the fixed channel state, which is just a constant, which is a many-body state in my space of the parent nucleus, where you create one nucleon on that particular orbit. So you can say this is equal to my state F, where you put one extra nucleon, a dagger with a creation operator, onto that particular orbit 1. So this is going to be my channel vector. And what I try to show you here is that if this is purely a one-body amplitude, so this A square is a single particle width gamma that you can compute in the normal mean field potential. So then if you would like to estimate your width, then for a given eigenstate, alpha. So what happens here is then you take your, in the perturbation theory, assuming the widths are small, then you take the expectation value between your W, of your W, and you immediately find from the factorized form that this width is a sum over all open channels of partial widths. And this partial width is just your single particle width for that particular channel multiplied by an overlap between your eigenstate and C, right? And this is called the spectroscopic factor. So it all comes from the factorized form of this W. If you put in the overlap, then you find this result. So this is commonly used in the shell model. If you are trying to estimate your decay, then you evaluate the probability through the spectroscopic factor of having a particle on that level, and you evaluate that from the many-body perspective, and you multiply your single particle decay width times essentially that probability. That would be an interpretation. And this comes automatically from this continuum shell model treatment that we discussed, and from Feshbach projection formalism. Okay, so in terms of approaches that we use, I'm going to mention that the problem with diagonalizing a matrix which is complex and energy dependent is not trivial. And often what happens is you have states that are very broad and states that are very narrow. And sometimes you have states that don't have any widths at all, which makes it a big problem because computationally you may want to know widths that are 10 to the minus 10, and at the same time you would like to treat the widths that are few MEVs. So in order to do that, the most natural representation would be in the time domain, where you don't have all of these problems disappear because you are just discussing the time evolution of states. And that reflects the actual physics. So what's written here is the set of arguments that suggest why time dependent is better, because you really have a time dependent, and you study the time dependence of the systems, then you have relation to observables. Then there is also linearity. As I mentioned, if you can avoid solving the eigenvalue, non-Hermitian eigenvalue problem in the time-dependent approach, which is related to absence of diagonalization. But let me demonstrate you the rest of the argument. So this is an example of this continuum shell model approach to study of the oxygen 24 resonances. So these are neutron resonances in oxygen 24 listed at higher excitation energy, and you see these resonances. So actually this cross-section was obtained from this picture, which is a time evolution of each of those states. So for example, if we look at 2 plus state, that's a 2 plus 1 state, this is here. So this is nearly a straight line because it's nearly exponential decay. Other states do not really decay exponentially. So, and for example, this state 4 plus 1 is a constant. So it's actually not decaying at all. So you don't see it here. Okay. So it's not decaying because of angular momentum conservation. So it's too high to decay to the ground state. So everything is, this channel is effectively closed by angular momentum. So you see all this evolution. Okay, now this model can be greatly expanded, and this is the example that we did some years ago. So this is a complete solution of all these oxygen isotopes. What is shown here is their states. So here we have states for different oxygen isotopes. And then for each of the isotope, we have a curve showing a cross-section for neutron scattering on, so for example, if I have here oxygen 21, that would be a scattering neutron on oxygen 20. So, and you see various resonances here. And the color shows the broader states. So eventually all these states are very broad. So this curve shows, of course, only the cross-section from the ground state. But all channels are open. So you can understand that this is a very complicated problem. First, you have to start from oxygen 16, which is the core here. and then you have to continue going to heavier oxygen isotopes. So each time you need a complete solution of your daughter system. So you need to know the channels. And in order to know the channels, you need to solve the lighter oxygen isotope. Then for each of the states, in order to find their widths, you need to solve this non-Hermitian eigenvalue problem. So you need to iterate enough times to assure convergence if you would like to discuss the width of each state. Right? And then if you would like to plot the cross-section, then you need to do, we can do a time-dependent approach, or you can actually do the inverse of the Green's function. So this is the process. Now there are many interesting things. Actually, it turns out to be very good from the experimental perspective. At the time we did it, the experimental information wasn't known, and now it's measured, and it's actually very good. So this is a new measurement which we predicted. So it's here. I would like to emphasize the role of this delta. So we talked about non-Hermitian part, this virtual excitation into a continuum. So, and this is the example of the effect. So this, what I show here is oxygen 24, and in the oxygen 24 there are two resonances of interest, which is 2 plus and 1 plus. So there are two curves here. The black curve is the one that shows the cross-section without delta. So when I don't have the excitation into a continuum and back. And this red curve that shows it with delta. And you see these positions are modified. So, and if you do this modification, then it seemed to improve the agreement with experiment. Okay, so this is another, just a model example of the role of continuum. So this is now the role of imaginary part. What it shows is the model. It's a simple pairing model that I don't really need to discuss. And we artificially set the threshold here at 0. And then we'll look. So the dashed line is a solution when we ignore W. And the solid line is the effect when we do have the W in the model. So, and you see that you get modification of the state. But because this is a threshold and we're talking about the part W, then of course once we below the threshold, then the traditional solution agrees with the one that has W, because the imaginary part is 0. Okay, so in the analysis of, I mean, all of this approach is very useful in the analysis of resonances and their interference. So what I'm just going to show you some more examples here. So there was this question of states in boron 8. There are various theoretical models that were predicting extra states, but these are the states in the continuum, and it was hard to determine where is this 2 plus, for example, state. So let me just demonstrate you. This is a time-dependent solution, and this shows, this movie sort of illustrates how you can modify your real Hamiltonian, essentially change the parameter V, and what happens with the resonance. So what will happen here is we're going to move this 2 plus around. So you see this is a cross-section at 2 different angles. These are the states. These are the resonance states. And this is the cross-section that you see. So in general, it's very hard. If you see this, how do you know where these are? Right? So it's a difficult problem. Now, but we can analyze that because we have different data on the cross-section. So let me show you how that, so this first movie. So I'm taking this 2 plus, and it moves, it interferes with another 2 plus, and then when it gets closer to threshold, it becomes sharper state. So effectively, eventually, it becomes a resonance. Right? So both cross-sections have peaks then. So this is one example. This is another example. So actually, it's a real experiment which was done by my colleague at Volya State. So this is the results of experimental results. So these are cross-sections at 2 angles. These are the states that many-body shell model predicts, but we don't exactly know what is the underlying interaction Hamiltonian. So these states are predicted at all kinds of energies, so they are not predicted precisely. So we would like to invert the scattering problem and match these cross-section with the states and with their interference. And as I showed you in the two-level example, matching cross-section really helps determining signs of interference. Okay, so this is example how we tried to do. We first moved 2 plus, it didn't work. We took the another one, and that actually did work. Then we moved 0 closer, and we got it much closer. So I ended the movie here, but I can show you the actual final result. So we had different interaction Hamiltonians that we have tried, and then we settled on the one which actually works very well. So, and we were able to obtain all resonances and their amplitudes, and the signs of these amplitudes was very important. So because of limited time, I'm not going to discuss the details of this, but if you modify any of these signs, then this cross-section will change dramatically. Okay, so then there is another effect, which is a threshold effect, which also appears, of course, in this model, because your model has unitarity, and as we discussed in the example yesterday, where you obtain cusps when other channels open. So this is a similar picture, which shows the flux conservation. So this is a reaction helium-6 and N. So these are resonances in helium-7. And what you see here is this is one cross-section, and this is a new channel opens of, so helium-6 has a ground state 0 plus, and the first excited state 2 plus. So when you have enough energy, then you can go to 2 plus, right? So it's basically this picture. If you start here, so this is your 0 plus, then you go up to a resonance, and then you can come back to a 2 plus. So this is going to be our inelastic channel, but you have to have enough energy. So starting here, you have a threshold, which opens new energy. And what here you see is a comparison. This is the inelastic cross-section that sharply rises, which is, again, similar to what we discussed yesterday. So it's the cross-section in the other channel. And this is the effect, this is sort of a cusp effect to the total cross-section that you see. Okay, so it's, yes? Oh, well, I called it little a, so which was a capital A there. So this matrix, as I said, is calculated in this actually straightforward way. So it's this discussion. So I have one particle from a particular orbit is removed from my parent state. So then in the many-body formalism, and which I'm trying to avoid discussing in too details, I'm removing a single particle. So there is a spectroscopic amplitude for a particle removal, right? So suppose I have, in this particular model, I have a p-shell. So I have my initial state I, and the particle is removed, which is acting a single particle annihilation operator in the second quantization language, from a p-shell, and it could be p1 half, p3 half. So let's say p1 half annihilation operator. And then I have a final state F. So this is my amplitude A, between my initial state I and final state F. So now, if I am talking about initial state as a basis state, I call this 1. So then it's an arbitrary state in my system, which is a basis state, removing one particle, going to a final state, and this final state is an eigenstate of my helium-6. So this state is my state in the helium-6, which is either 0 plus or 1 plus. So this is my matrix element for what I call spectators, because from here I just remove one particle from an orbit. Then I need the actual overlap of my magnitude, and that one I called little a, which was a function of energy. Well, I can call it a, well, let me still call it a little a and define you what it is. So this single particle gamma of energy is just little a of energy squared. Right? So, and this, as we discussed before, is the matrix element for my only one particle, which is actually moving, for my potential V, energy representation state E, and my initial state, which is P1 half. Magnitude squared. And I'm not writing 2 pi here, so, but it depends. You can renormalize this E not to have 2 pi. Okay, so basically speaking, my amplitude A is constructed as from a many-body part of everything that doesn't move, or of spectators. And my single particle is removed because this is a one-body process. This single particle is removed with interaction V, which is Wood-Saxon eventually. So I compute this numerically for a Wood-Saxon potential that matches my nucleus relatively well. And then I multiply it by a shell model component, which is this spectator overlap, essentially, or fractional parentage coefficient, more precisely. Okay, so this is how this A is computed. All right, so I think in the limited time, I also wanted to discuss about the two-body decay, which is an interesting story. But it turns out that in the oxygen 26, if I magnify it, this state is slightly above. But it can't decay directly because it has to do this and this step, or go through virtual. So it has to go through virtual states, and then it's interesting to discuss, if I have 3 states, if I move my middle state up, so let's suppose my state number 3, the final state is at 0, this state is energy 1, and the state number 2 is moved. So this is a calculation of the decay width. In the classical case, if I'm moving the state 2, state 3 can decay to 2 and then to 1. So in the classical case, the decay will be forbidden once I'm reaching this point. So once I'm at 1, the decay becomes forbidden. But of course, in quantum mechanics, this process is possible. I can go up and then down again. So, and this is the calculation in some example, I think for D wave, that this is the classical answer, it goes to 0. This is a decay in quantum case. When in this situation, both are pretty close, right? So how is it calculated? It's calculated for the same amplitudes. It's just now I have the full decay amplitude is a product for the first step times the second amplitude divided by, again, the propagator in between, which is the energy difference. So it's again like a second order perturbation theory. Okay. Now, if you deal with S waves, then things become a mess, and it doesn't work for S waves. So this is example of classical and quantum decay when I have an S wave decay. So 2 particles in the S state will decay completely differently in the quantum mechanical case. In addition to that, there is also an interaction. If these are 2 identical particles, there is a problem with symmetry, which has to be discussed separately. All right, so I think I'm getting close to being out of time. So this is where we use this kind of sequential decay also besides oxygen. There is an interesting experiment of decay of beryllium-16, which shows 2 neutrons coming almost in the same direction. So in 2 neutrons come almost in the same direction. This happens because their neutron-neutron scattering length, as we discussed in our earlier lectures, is very large. So they can get correlated, and then therefore they come in the same direction. Some quantum chaos studies, so when I have many of these resonances, and I have a channel, then I can also think in the sense of chaos that my many-body vector is randomly oriented in the multidimensional space. Then if it's randomly oriented, then the distribution of amplitudes between my channel and my state is just like the direction in multidimensional space. So then this direction becomes a Gaussian distribution, and when you square it, it becomes a Porter-Thomas distribution. So again, you have a homework exercise to study this. So, but what turns out that actually there recently been deviations observed from this Porter-Thomas distribution. So, and then the question arises, why there are these deviations? And there are several examples that we can consider. Yeah, these are the results. But there are several examples, or there are several possibilities. One is the overlapping resonances. Another one is the memory effect. So that your state, as we were talking about our discussion with the multi-channel S matrix yesterday, it essentially says you form a state, and then the state forgets about how it was formed. It just decays proportionally to different widths. Now, that can be modified if the state doesn't forget how it was formed. So, and this happens in particular if your interaction is only a few bodies. So, for example, two-body interaction where you allow only two-body scatterings may be slow enough to mix everything and to forget what was in the past. So this is one of the reasons this can happen, and I guess I can address these papers if you want to study, and do your homework, because that will give you an idea about this. I also wanted to talk about clustering, and maybe I'll spare a few minutes to mention. So recently we've been doing a lot of work with this approach related to clustering, and I already alluded to an important phenomenon that has been observed, is that if you have an alpha and states somewhat separate into different types of states, one that have broad or strong alpha structuring or alpha clustering, and the other states that do not have a strong clustering. And it's hard to understand it because usually in the many-body physics, everything should be mixed. So again, it's an example where things are not strongly or mixed strongly enough. So what is shown here is somewhat Kata diagram, which you already seen here, just presented in the other way. So there are many interesting structure cases. Beryllium-8 was mentioned that it's very close to the alpha threshold, which is shown here by dashed line. Then this one, beryllium-10, is interesting because this is like a molecular state, and this molecule of two alphas bound by two neutrons can rotate as well. So now it has a rotational degree of freedom. Then, of course, carbon-12 with famous state 0 plus above the threshold, and then you can have oxygen. And also there is an interesting discussion about this rotational band. So ground state and oxygen believed to be not strongly clustered, but there is a rotational band argued to be as alpha plus carbon-12, which is shown there. So how that can be studied, it's a complicated process. Now you have to make a alpha channel. Alpha channel is difficult to construct. It's not similar to this channel. It's not a one-body channel. So the way we do it is what is shown on this picture. So we have an original daughter nucleus, and then we make a 4-nucleon state somewhere else. And we position this 4-nucleon state to have a correct center of mass motion relative to the core, so which is described here. So in fact, we think in terms of the harmonic oscillator basis. So for example, in SD shell, each nucleon has 2 quanta in the oscillator. Then these quanta are additive, so we have 8 total of quanta. We can rewrite this wave function as a center of mass with 8 quanta, and intrinsic system having 0 quanta. And we can model this intrinsic system with 0 quanta as s to the 4th, which is our alpha particle. So then there's some complexity about the center of mass and Mashinsky transformation that I'm gonna skip. The important difficulty in this story is that these channels are not orthogonal anymore. So all of my story here was the channels were orthogonal. If I take 2 channels, I remove one particle from a given shell, or I remove another particle from another place, then these channels are definitely orthogonal. With alpha, they are not orthogonal. An example of that is if I put 2 alphas on the same space, then they are almost bosons, but they are not bosons. So you can evaluate this operator. So if my psi is the alpha operator, then or phi, then phi dagger measures the number of bosons. So this expectation value for bosons should be just 2. Now, if I put 2 alphas on the SD shell or on various shells, so for P shell I get this number, for SD I get this number, and so on. So they are not 2. So therefore, it means that there is an overlap between these 2 alphas. So these channels are not orthogonal, and that's the core of the story. I guess I'll go here. So what you need to do is you need to add to your Schrödinger equation what we call a norm kernel. So you no longer have equation which is H psi equals E psi, because this equation implies that, or in the matrix form implies that these possible states are orthogonal. So then you have to solve an eigenvalue problem where you have energy times some norm operator times psi. So, and that is the discussion that I'm showing you here. Okay, so maybe I should... I have to do this norm matrix. So if my states, so if I'm doing H1, 2 in terms of states 1 and 2, and the states 1, 2 and not orthogonal, then I have to calculate N1, 2, which is just an overlap between 1 and 2. Yes, it's a regular norm kernel. But now it's complicated because this is a many-body. So these channels, they contain many, 4 particles, each one. So I'm calculating a norm kernel out of all those particles. Moreover, I have to do it, if I would like to do reactions, I have to do it in the coordinate representation. So therefore, there is also a running distance r. So this norm, instead of being an overlap, it becomes actually an operator, n, that depends on r prime. And when I do this action, then I'm just integrating over one of those variables. Okay, so as you can imagine, this reaction problem now becomes much more complicated from the reaction problems that we have discussed before. Okay, but I just wanted to mention you where things are. So these are various studies. These are spectroscopic factors. So these are just overlaps. As again, spectroscopic factor would be if you assume channel, the W is very weak, then in that limit you can just do a perturbation theory. So, and you can evaluate this widths through the perturbation theory, and the width is a product of the phase space energy dependent part multiplied by the spectroscopic factor. So, and these spectroscopic factors are shown here, and in fact some can be compared with experiments. So this is for alpha emitted from magnesium 24 in partial wave with L equals 6, just as an example. We did that also for carbon 12, and this is the spectrum of carbon 12, experiment theory, and these are various, this is the rotational band shown here with electromagnetic transitions, and this is the corresponding strength, so 0 plus is in red. This is corresponding spectroscopic factors essentially for that case. And these are different channels that we have considered. And I understand that, of course, it's very hard to comprehend everything, especially when I'm showing PowerPoint. So if you have questions later about specific details, I would be happy to answer that. Okay, so anyway, I would like to conclude, and I think it's time that I conclude. So that, of course, atomic nucleus is an open quantum many-body system. This is almost my slogan, because open means we do reactions, and it's quantum because quantum mechanics is important, and it's a many-body system. That's what makes it interesting. And what I also think, we're lucky to do nuclear physics because it nowadays emerges as almost a central discipline. I do a lot of work and a lot of research related to quantum computing, related to quantum chaos, and it's all related. For example, in computing, when you have qubits, What you need to know is how long do these qubits live? What happens if you do a measurement? How do the states survive? And you would like them to survive. So you have to actually look at the open system, because otherwise if it's closed, then you have no access to it. Then it's not interesting because you can never see it. All right, so then of course there is a lot of components related from fundamental theory to applications, and another interesting avenue is high performance computing. So now I'd like to thank the support of the school, support of the Department of Energy and Florida State University that made my visit here possible. And I also recommend, using this opportunity, we're finishing a book which is going to be published soon about atomic nuclei. So not everything related to reactions will be discussed there, but there will be a lot of hopefully interesting things for you to read in there. And I thank you for your attention. Oh, you have questions? Good.
So you kept the book as a surprise.
I'm glad, yes.
This is why when I asked him for notes, got one. Okay, so if you have some urgent question, we can discuss a bit. If not, after lunch.
Sure. Okay, so with respect to first question, of course, gamma spectroscopy is a completely different story. So you're looking here usually at the states that are stable with respect to nuclear forces. So you're looking at stable nuclei. Now, when you would like to understand the systems that are not stable, for example, what I was discussing, then your nuclear decay happens much quicker before any gamma. So you don't see anything. There are very few cases where you have competition between gamma and a nuclear. So we're talking about really unstable system in the nuclear sense. Right? So that's a big difference. Now, on the other hand, this ability to observe resonances, as I was trying to emphasize, helps us in some way, because when they are broad, they overlap. So in the gamma spectrum, where if you have two resonances, 1 and 1, they are far away from each other. So you only know the widths, and you know the square of the spectroscopic factor or corresponding E2 matrix elements or something like that. When we have broad states, then they become broad and they overlap here. And when they overlap, it depends on their relative signs. So this behavior of the cross-section here can be very different depending on the signs. So, and that gives us extra information about the structure of these states, which we cannot infer just from their positions of states and from their widths. Okay, so this is something new that we get. Now, for your second question in terms of model dependence, of course there is a lot of model dependence. And one of the reasons I show you this example where we fit the position or which state is, because we had three different models. But looking at what is observed, we can nail the right model or find the right model and say, well, this is the right interference, and then we can work backwards and try to understand something more fundamental about that physics. Why is it so? Any other questions?